Hello everybody, we are now on the second activity in the momentum module. We're going to concentrate on conservation of momentum and 1D collisions. And within one-dimensional collisions, there's two types of collisions, elastic and inelastic. Okay. So if you haven't begun reading, start in Coletta, Chapter 8, and try to get some of that reading done. Also, if you haven't started, please start your homeworks in Sapling. Homework 10 if you're in Physics 111 and Homework 7 if you're in Physics 121. And this content is related to Lab 10 and 11. Okay, so in the last chapter we had learned about momentum. We learned about the conceptual understanding of momentum, conceptual understanding of impulse, and how that's related to force diagrams. We also did a little bit of work with force versus time graphs and how you could identify impulse from force versus time graphs. And we also worked with momentum bar charts. Well, now we work with momentum bar charts to create equations and solve for things. Well, now we're going to use all of those skills here. And starting off with conservation of momentum. So the law of conservation momentum basically is this. If there's no external force to a system, then the momentum within the system should remain unchanged. And so what does that mean? Well, let me get my tablet out. Let me go ahead and start with a little drawing here. We learned that impulse, which is this J vector, which is is a force times change in time, that is equal to the change in momentum of an object, right? I should use I. These are all vectors, right? Well, what we're finding out is, well, this is an outside force. This is a force leaving the system. So this right here, this force in the impulse is a force outside the system, right? So if your system is just a ball, right, and this ball is not moving, it's just sitting on the ground, okay? Okay, well, the ball's going to just continue sitting on the ground, not moving, okay? So you need an external force from this system to have it change its momentum. These are initials, right? So you have to have an outside force drive this thing, like a hand or a rope or something like that, push it, which then will then give it a velocity vector to the right, and will also give it a final momentum. Should put vectors on all these guys too. Okay, so this is a force outside the system. Well, if there was no force outside the system, what that would mean is that P, the final momentum, would be equal to the initial momentum. Okay, and so what they're saying is that the initial momentum is equal to the final momentum, and that is because the total change in momentum to that system is going to be 0. Okay? So that's kind of the law of conservation of momentum. And you probably heard me talking about it a lot, okay? And this is a representation of that. So the system isn't going to change. The particles in that system aren't going to change. Whatever momentum's in that system is not going to is going to stay in that system, right? Unless an external force acts on that system, or some of that system has a force that will leave that system. So I'm talking about a system a lot, and just like the last the last activity, 4.0, you have to establish a system when you're talking about momentum. And also, same, I guess similar to the energy stuff. There's a system in play, and if energy is leaving that system or energy is entering that system, that's going to change how you have to approach the problem. So momentum, like energy, is all about establishing what the system is. Okay? So here we have an example of that, right? So if you have a ball, if you've established the system is just a force around this ball, and you're only looking at the ball and you're not caring about what is outside the ball, then that system is only going to be relative to the ball. So here's an example of this. So suppose you had a ball that is initially not moving. So it's got an initial velocity that is 0 and an initial momentum that is 0, right? Well, now, if your system, now you bring the Earth out into play outside the system. Well, now the Earth is going to act on the ball and give it a force down. It's going to give it a force. In other words, it's going to give it an impulse, right? And I'm giving it 3 blocks, and I shouldn't color that in. I should show that it's 3 blocks, right? So the initial momentum is 0, right? And now you have a force acting on this. Well, it's going to give it three blocks, and I'm just giving it 3 blocks. It's subjective. And then a little bit later, this system is going to show this ball is now got a final velocity down, and it will also have a final momentum down. Make sure I put vector heads on everything. And so now that we see that this thing has a momentum towards the Earth, and I'm just going to call down as positive, okay? The force is directed in the same direction, okay? So I'm kind of, in this case, I'm doing something different. I'm calling, in this case, down is positive and up is negative. I'm just making it the math work out. And so what that'll mean is that this ball afterwards, even though it was not moving or has 0 initial momentum, an outside force acted on it, and that's what impulse represents. Again, impulse is force over a period of time, and it's still acting on it here. But it's going to have a final momentum just moments later right here. Okay? So it's about establishing the system. Well, there's a better way to do this problem. Rather than just looking at the ball itself, why don't you make the entire system, both the Earth and the ball? Okay? And so here, if you do this, you could set it up that the initial momentum of the ball was not moving, and that the initial momentum of the Earth was also not moving. Right? I'll put a little O for the ball. And maybe let's put a B. However, both objects were put in the vicinity of each other, okay? And this is an interesting problem because now the Earth is going to be moving up to meet the ball. So its final velocity is going to be up to meet the ball, and so its momentum for the Earth is going to be directed up to meet the ball. And here, the ball is going to have a final velocity and a final momentum down to meet the ball, right? So now this force is inside the system, and since it's inside the system, this impulse is an outside force, outside force entering in the system or an inside force leaving the system. Well, since the force is contained in the system, you have to start out, so that means there is no impulse, right? The net force, this force up, is equal to this force down, and so that is 0, right? So that's what impulse is. It's a net force of the system, okay? Well, the ball, and I'll put ball, and then Earth, there is no initial impulse for the Earth or the ball. However, the ball is going to have a downward momentum, and the Earth is going to have an upward momentum, going back to the regular system. Okay, I'm establishing my coordinate system. Okay, so that means if the Earth had 3 blocks of if the Earth had 3 blocks of momentum up, and this is 0 here as well, I'll just put a little 0 to mark those, then that means the Earth is going to have 3 blocks of momentum down. Because again, the momentum in the beginning here plus the impulse, that's just that impulse equation, has got to be equal to the final momentum, right? And so if there is 0 momentum in the beginning and there is 0 impulse in the beginning, then the final momentum total, and I should do a total on this, has got to be equal to 0 as well. Gonna erase that sum. So this would be negative, let's say negative 3 blocks is a negative 3 kilogram meter per second plus 3 kilogram meter per second, right? I should remember to put my units on things. Kilogram meter per second. So that means this 0 has to be equal to 0, right? Well, as long as the system is contained, all the forces are contained in that system, just like in this case, then you just basically, rather than worrying about a J vector, what we are basically saying is the sum of the initial momentum has to be equal to the sum of the final momentum. And as long as all the forces are contained in the system, the net force on the system, right, this is going to be a negative force down, and this is going to be a positive force up. Well, the net force is going to be 0, which is what impulse is. It's also the net force on a system. In this case, that you have a negative Fe plus Fe, and that's going to be equal to 0, right? The difference here is in the last case, there was a net force, and that net force was greater than 0. Okay? So that's what, this is kind of how we're going to be using bar charts to analyze a system and to create equations. Okay? So again, as long as there is no net force, as long as the net force within that system is 0, meaning there's no outside forces coming in or inside forces leaving that system, then the initial momentum is going to be equal to final momentum, and thus the total force within that system will be 0, right? So that's the reason why we could write that, and that's why this is why the law of conservation of energy makes sense. Well, there's a lot of examples of this case, and we're going to do a lot of these examples as problems in a minute, but one idea of when a cannon is fired, the force on the cannonball inside the cannon barrel is equal and opposite to the force of the cannon on the ball, right? So this is an extension. This conservation of momentum is an extension of Newton's third law, right? So the two forces are gonna ball's gonna be sent flying to the right because the force of the cannon on the ball is going to be a positive force. Now the cannonball is also pushing against the cannon, which is going to have a force to the left, right? And the cannon is going to move really fast again. So even though the two momentums of the cannon and the ball are going to be equal, right? So it's going to have a positive force to the right. Okay, so even though the momentums are equal and the forces are equal, the velocity of the ball is going to be huge, right? Because it's got a little itty-bitty mass, right? Well, meanwhile, over here, again, the cannon is going to have an equal momentum to the right, right? And that's a P. So this is the momentum of the ball, and this is the force of the cannon on the ball. Okay. Well, over here, these arrows are opposite, but the same magnitude as these two arrows. However, this guy's velocity is going to be a lot smaller, right? Because it's got a huge mass. Right? So even though the momentums are equal, that doesn't mean that the velocities are equal. Okay? Just draw little vector heads on all this stuff. So this is a cool example that just brings everything together, right? The concept of impulse, Newton's third law, and momentum. Another type of system that you could think about is that the molecular forces is more of a microscopic system. Is when a ball gets hit, or is jarred, all the little molecules are contained within that ball. The ball doesn't explode, right? So they get jarred, so the kinetic energy stays within that system again. So this works for large system and small systems, right? So if you thump, if my hand, basically if you thump a baseball and provide an outside force, and now all the little molecules are moving in there, well, all that kinetic energy is going to be contained within that ball, right? So they're all bouncing off each other within that ball, and nothing leaves the system, okay? So overall, this is what what we're saying is the conservation of momentum is at the initial momentum before. So now we're going to get into collisions. I should back up a second. We're going to get into collisions, okay? And so this concept of conservation of momentum is going to be very important. And so we're going to be looking at the momentum before a collision. The total momentum before a collision is going to always be equal to the momentum after the collision, so long as nothing comes from outside the system, no impulse or force comes from outside the system to alter the system. Okay? So essentially, in a more drawn out point, if you have 1, 2, 3 different types of objects, their sum of all of those momentums, their initial momentums before a collision, should be equal to the sum of the momentums after the collision. And not only that, later on we're going to get into two-dimensional momentum problems, right? Right now we're just going to be dealing with one dimension, which means just along the x direction or just along the y direction. But this works for both in the x and y directions, okay? The initial momentum in the x direction is always equal to the final momentum in the x direction of a system, of a self-contained system, okay? And same thing for the y direction stuff. Okay, so here is a basic tutorial of what we're going to do is we're going to read very carefully. First of all, we're going to read the problem. And then we're going to try to storyboard or sketch the problem. We're going to make sure when you are sketching the problem and drawing velocity vectors and momentum vectors that you are drawing them in line with an established coordinate system. I'm going to typically, 99% of the time, I'm going to say to the right is positive x, to the left is negative x. So any vectors pointing to the right are going to be positive. Any vectors pointing to the left are going to be negative. Okay? And then once you draw those vectors and you draw the little masses and storyboard everything, you're going to make sure you got to subscript those things as initial and final. If there's two objects, maybe like A and B, or 1 and 2, or you could even label it like a force of a block and force of a hand or something, right? So you could even subscript it with the actual name of the object, right? And then what we're going to do is we're going to list out what we know. So so we're going to list out what those symbols are. And actually, I'm going to try to actually put in what the actual velocities are. If they're just whole numbers, it's actually really easy to work with that, right? So you're going to actually list out what you do know and give it the numbers. And then you're going to list out what you don't know. And one more step here that isn't added here that should be is then we're going to make momentum bar charts. To help us construct the equations. Okay? And once we know that, once we do that, then we're going to construct the equations. And then solve. So, and it's typically, with one-dimensional problems, they're kind of easy because there's only one equation, so there can only be one unknown. Okay? Well, here we go. Let's start with elastic collisions, okay? So the first type of collision we need to learn is elastic collisions. And that means bouncy, objects that bounce off each other. Inelastic collisions, which we'll get to in a second, are sticky objects. When they hit each other, they stick together. Inelastic meaning opposite of elastic. So when we are doing these elastic collisions, we're going to only consider the fact that the collisions are perfectly elastic, means there's no loss of energy to heat or sound. Okay? And here's an example that what we're talking about. Suppose you had ball 1 that had a positive momentum to the right, ball 2 that had a negative momentum to the left. When they hit, they are going to be providing equal and opposite forces, right? Objects, forces are always equal and opposite, Newton's third law. And so when you look at the net force on this is one force to the right, this is one force to the left, and it's the same force, they'll nil each other out to be 0. Then after the collision, so that what this means is the J vector is 0. The sum of the J is no net force is leaving or entering the system, as long as the sum of the system is 0. So after the collision, now ball 1 is going to have a negative momentum and ball 2 is going to have a positive momentum, right? And this looks like both of these masses are equal. Well, they may be equal. These green vectors are supposed to represent the momentums. So I'm not sure. But basically, if they hit each other, as long as this thing isn't a supermassive object, they will bounce off and go in the opposite directions. Okay? Okay. Well, let's do a problem similar to that, but here's what we're going to be seeing, okay? We have a 5 kilogram car moving to the right at 15 meters per second. So this is a 5 kilogram car. And I'm going to actually put my variables in here. So this is a 5 kilogram car. And this is actually, I will put the masses below this. That'll be cleaner looking. Okay. And small m is 5 kilograms. Okay. So before the collision, this has a velocity to the right of 15 meters per second, right? Well, that means that it had an initial momentum, which is 5 times 15. So what is that? 2, 4, so 6. So 4 of those is going to be 60, and 5 is going to be 75 kilogram meters per second. So this is 75 kilograms meters per second, and I got that from 5 kilograms plus 15 meters per second. 30, 60, yep, 75. All right. Now, this 10 kilogram car, which is the capital M, okay, and over here, I'm going to give this a small m, and this is a capital M, small m, capital M. Well, this capital M car, before the collision, okay, it says if the second car has a mass and a new speed to the right of 20 Okay, so initially the looks like it is moving to the right at 10 meters per second, and then the first car, the small m car, overtakes it, right, because it's traveling much faster. After the collision, this 10 kilogram car is going to be traveling to the right at 20 meters per second, and that's going to be positive. So this guy had a momentum to the right of 100 kilogram meters per second. Okay. And afterwards, it's got 200 kilogram meter per second. So I'll summarize what's going on. So from me reading this, what I try to do is I try to diagram. So the diagram was already given to us. Okay. So it looks like we have a 5 kilogram car that's traveling at 15 meters per second. It overtakes a 10 kilogram car traveling at only 10 meters per second, right? After there's a collision, the 10 kilogram car is now traveling at 20 meters per second to the right. And we need to know what is the final velocity of the 5 kilogram car after the collision. I put the momentums up here to kind of help me gauge how many blocks I should be giving this stuff, right? So I'm going to try to also graphically analyze this, okay? So it looks like the initial momentum of the first car is going to be, let's say, 2 blocks to the right. So unfortunately, this 2 blocks represents 75 kilograms meters per second. Actually, let's say this is 1 block. Let's say this goes all the way to, this is 200. So this is going to be 100, halfway part, and we'll say this is 75, okay? So I'm trying to establish a scale here. And the big car had a 100 kilogram meters per second to the right, okay? So it had 2 blocks. Well, after the collision, okay, it's now traveling at 200 kilograms meters per second to the right. Okay. And for that to happen, this is 3 blocks, is going to be equal to 4 blocks. That can't make sense. So this has to have a -1 block for that to happen, right? So I'm predicting that this one mass object, by me graphing this, right, and kind of putting some stuff to it, it's going to have a negative momentum, which makes sense. Its velocity's got to be negative here. And that is going to have a negative, which is actually going to take away from this guy's momentum. And so we learned that initial momentum has got to be equal to the final momentum, since the j vector here is going to be 0, where all the momentum, all the force are contained in the system. There's nothing from outside adding to this. So let's go ahead and copy down what we're seeing. Okay, we have the initial momentum equal to, actually the total initial momentum is equal to the total final momentum. And so the initial momentum of the ball, a block of the one mass object, the small guy, plus the initial momentum of the capital guy, that's going to be equal to the initial momentum of the the final momentum of the small mass guy, plus the final momentum of the capital guy, right? And now I'm going to put in, well, we don't need to do that because we wrote our momentums up here. But what I'm going to do is I'm just going to say small m I, right, subscripting the mass to be the same as the momentum there. And then we have capital M times the velocity of the capital M initial. That we should make that distinct. And that's going to be equal to the small mass guy and his final velocity plus the capital M and his final velocity. Okay? And we're going to have to solve for this, right? So what we have to do is bring this entire thing onto the other side by subtracting it. Okay? So mv of the little guy, just copying this up here, plus capital M V and his initial minus capital M V final, right? This guy is now on the other side and it's negative. And that's going to be equal to the small m and his final momentum. I'm not designating this with a negative, even though I know it's going to work out to be negative, and it has to, for this to, if this is 3 blocks here and 4 blocks here, this has to be a negative momentum, and how that gets it is from this being a negative. But I'm just going to leave it here as positive, and this hopefully should work out. Well, now I have to divide both sides by that small m. Small m, and that is going to be our velocity here, right? Well, I'd worked out these momentums here earlier. This is 75 kilogram meter per second plus 100 kilogram meter per second minus 200 kilogram meter per second. Okay. This total right here is going to be 75 plus 100 minus 200. So this whole thing is going to work out to be, I don't know why I changed that to this. So this is going to work out to be negative 25 kilogram meter per second divided by 5 kilograms. 5 kilograms. And that's the final velocity of the small m object, right? So 25 divided by 5, what is that? Well, that is going to work out to be, I'm running out of room. That is going to work out to be negative and now I'll do this in red so it stands out. So the final velocity of the small mass object is going to work out to be negative 5 meters per second. Okay, so this is going to work out to be negative 5 meters per second, because negative 5 meters per second times 5 kilograms is going to be negative 25. And that means this has got to be negative 25 kilogram meter per second, because this is 200. This is 100, positive 100. And this is positive 75. So, makes sense. And that's kind of how you walk through a problem. If there's no picture given, you draw it. Then on your labels, make sure you label it appropriately. Establish coordinate system. To the right is positive, to the left is negative. Then fill in your knowns and fill in your unknowns. Put a question mark next to that. Okay. Create a momentum bar chart. And then go ahead and copy everything down. See, by the time I get to here, I've already had an idea what this should be. And this just kind of helps me out with the math to confirm it. Okay? That way you get it done once, you get it done right, and without many questions. So, good problem. Let's try another one. This is a bit of an easier problem. Okay? So, I want you to try this on your own using what we just did. Okay? So, go ahead and read the problem and draw on your values. Put the pluses and minuses. Try to put the momentums on there too. Fill in your bar chart. And then go ahead and try solving it. So try to do the whole thing, and so let's see what you get. Go ahead and pause the video now. All right. Well, let's go ahead and read the problem. We have a 2 kilogram mass object. And so this is 2 kilogram mass object. It's moving to the right at a positive 9 meters per second. Okay? It makes a perfect elastic collision with a massive object at rest. A big M object at rest. The 2 kilogram object is going to recoil at negative 4 meters per second. It says it's going to recoil, so I'm assuming actually it's going to recoil at a speed of 3 meters per second. Okay. While the big mass object is going to be moving to the right at 4 meters per second. Okay. In the beginning, it also says that this guy was at rest, so it has no momentum. So, what I like to do is, it looks like the question is, what is the mass of the object? So mass is unknown of this object, but we do know the mass of the smaller object. Okay, so it's one unknown. We can do it. What I'm going to do is I'm actually going to I'm going to get the momentum of this 2 kilogram block, and so that's going to be 18 to the right kilogram meter per second. This is going to be 0. After the impact, it looks like it's got a velocity vector to the left, and so its momentum is going to be negative 6 kilogram meter per second. And this guy is going to be to the right at 4 times the mass. So this is going to be a capital M, 4 kilogram meter per second. It's going to be 4 times that. Let me write that a little bit more legible. So 4 mass kilogram meter per second, right? So whatever this mass number is, it's going to be 4 times that, okay? Well, let's go ahead and fill this in. Okay, this is our 2 kilogram object. This is our 4 kilogram object. 2 kilogram object, 4 kilogram object. You could I could have labeled these A and B, but I like actually putting the number in too. So let's say before the impact, this sucker was 18, right? So I'm going to call 4 blocks as 18. Okay, and the reason why I gave it 4 blocks is 18, because 6 is divisible by that. So if it's a total momentum is 18 here, it's going to be 18 here total. And then after the impact, this guy is going to have a -6. Actually, I should have used only 3 blocks. That way, if this is 3 blocks, this is 1/3 of it. And after the impact, well, this has got to be now 4 blocks here. So this is positive, this whole thing has got to be positive 3 blocks, right? Which this is, actually, I'll just put the actual number. Before the impact, this was 0, right? So this is going to be, before the impact, it's positive 18 kilogram meters per second. The total initial momentum is this. Well, in the end, it's got to work out to be total of 18 kilogram meter per second after the impact, right? And this is going to be positive 18 meters per second, right? So I'll use red to put that above this and try to fill in. So this is positive 18 kilogram meter per second. Well, if this is -6 kilogram meters per second, and I know this is going to be 4 kilogram meters per second. Well, if this is -6 and this total has to be 18, then what this has to be a positive 24 kilogram meter per second to make up for that, right? So I'm going to go out on a limb and say that this 24 kilogram meter per second divided by 4, right? If the final momentum of that is going to be 24 kilogram meter per second, and that's going to be capital M times 4 meters per second. What is that? 24 divided by 4. Well, what that means is 24 divided by 4 kilogram meters per second divided by meters per second. That's got to be equal to 6 kilograms, right? So that M has to be 6 kilograms, right? So I'm going to guess that this has got to be 6 kilograms. Well, let's confirm our suggestion, okay? Always start with the sum of the initial momentum is equal to the sum of the final momentum, right? Okay. I've got to make sure I put a little vector on that guy. And that I'm just going to go ahead and put in the variables here. The 2 kilogram object and its initial velocity plus the massive object and its initial velocity. And I'll put a 4 here. 4 initial, and this is 2 initial, right? Is going to be 0, right? That's going to be 0 because it's not moving, it says in the problem. Well, after the impact, the 2 kilogram object has a negative final velocity, and the massive 4 kilogram object has a velocity that is positive. So it's positive there. Well, this is going to be 2 kilograms times 9 meters per second, it's positive, plus 0 kilogram meters per second equals 2 kilograms times a negative 3 meters per second plus the mass of this object times a positive 4 meters per second. Okay? So I've got to bring this negative 6 kilogram meters per second onto the other side. So I'm going to actually just put in the momentums here first. 18 kilogram meters per second plus 0 kilogram meters per second. And that's going to be equal to negative 6 kilogram meters per second plus m 4 meters per second. Okay, I've got to add this 6 to the other side. When I do that, this is going to become 24 kilogram meters per second equals the mass of the object times 4 meters per second. That should be a 4, right? Divide 4 by both sides, and it's starting to look like the exact same thing that we had above. Equals 24 divided by 4, that's 6 kilograms, which is the mass of our object. Yeah, so it looks like we're right. Pretty cool. So that's how you use all three of those, you use all those tools that you're given to actually solve each one of these problems. And I really do urge you to use the momentum bar charts, right? Because that lets you see what the momentums are. And I actually like inserting in our momentum vectors to kind of help with the problems here. Because after I just wrote down the numbers here, I actually was just looking up at what we'd already done here. So, and that helps really get you thinking about these problems. All right. Well, let's move on to inelastic collisions. Okay. Again, inelastic collisions are the opposite of elastic collisions, which means instead of being bouncy, they're going to be sticky. So when they hit each other, you got object 1 and you have object 2. They're moving at each other with differing velocities. When they hit, then they're going to stick together and they're going to have one common velocity and a combined mass. Okay. So what I like about these problems is rather than having two velocities afterwards, you have just one velocity and the combined mass of both objects. Okay. So let's do a problem kind of similar to the last problem that we did, except this case the objects are going to stick together. And also what's really cool is this is a multiple choice problem. All right. So what I want you to do is now I want you to storyboard the problem, getting a diagram, drawing the velocity vectors, writing in the masses, labeling the masses. We'll call object A as the 1,200 kilogram car, and we'll call object B as the 1,500 kilogram car, right? And what I want you to do is I want you to do a storyboard, label the velocities just like we had done, go in, fill in the momentum bar charts, and try to, do the part and figure out what the combined velocities of both objects after the collision is. That means you're not going to have two separate bar charts. You're just going to have one bar chart of both mass A plus mass B. So just one bar chart, okay? And so what I'll do is actually cross this out, and this is A plus B. Okay? So don't worry about this guy. All right, so we're not going to put a bar here. Anyways, so go ahead and try it out and hit pause. Okay, we're back. So let's go ahead and storyboard what we're seeing here from this problem. Okay, so we have a 1,200 kilogram mass car. I'm going to call it A, and it's got 1,200 kilograms. And they said it's traveling to the right, and it's going to collide at, it's got an initial velocity of positive 15.6 meters per second. Draw that in a more legible mass, meters per second. Okay, it's going to come, the object B is stationary, and it is 1,500 kilograms, and it's got an initial velocity that is not moving. So the equal sign is the impact, and so A and B are now moving together. They're locked together, and they're a total of, what is that, 1,200 kilograms plus 1,500 kilograms. What is that, 2,700 kilograms? Sounds good. And they're going to be moving together with some unknown velocity after the collision. Okay. Well, here we go. 1,200 kilograms, 15.6 meters per second. I'm going to draw the momentum vectors on this. So 1,200 kilograms times 15.6 meters per second is 18,720. So it's got an initial momentum that is 18,720 kilogram meter per second. And that's the initial momentum of this guy to the right. And it'll be positive. This guy has a zero momentum. Afterwards, both of these guys are going to have a final momentum that is going to be 2,700 kilograms times their final velocity, right? And so I've labeled everything. I've got an unknown right here. Here's my unknown, is the final velocity. And hopefully it'll end up being one of these numbers. We'll find out. But let's jump to the momentum bar charts. And if you haven't done that, go ahead and stop it and do it. Okay? Right now. Please. Okay. So we know it's going to have 18,720 kilogram meters per second of initial momentum. And I'll just give that, sure, we'll call that, like, that's about 20, right? 20,000 ish. So 4 blocks is 18,720. Well, in the end, if the first object, okay, so I'm going to draw those momentums here. This represents 0 kilogram meters per second, right? And this represents 18,720 kilogram meters per second. Okay. Well, in the end, with the combined masses of these two, and this is the combined mass, A plus B, of both objects, that has to also have a final momentum that is equal to the total initial momentum. So the total initial momentum is a positive 18,720 kilogram meters per second total. This plus 0 is this, right? Well, that's got to work out to also be 18,720 kilogram meter per second, right? Well, the only way that could happen is with these two combined masses, that works out to a total momentum of that per second. So that whatever the final velocity is, it's going to be basically 18,720 kilogram meters per second divided by 2,700, right? So divided by 2,700. So it looks like the final velocity is going to be around 6.933, right? 2,700 kilograms. So V final is going to be equal to 18,720 kilogram meter per second. I'm just doing a prediction. 2,700 kilograms. That's going to work out to be about 6.93 meters per second. That's what I'm guessing. Okay. That's before I've done any formal methods using this. So let's start off creating our equations again. And again, you've got to state that since the entire system is the system, it's blocks A, blocks, and block B. Okay, that's the system. There's no external system to this. Well, its initial momentum of block A and the initial momentum of block B, that's equal to the final momentum of both of them combined is this. Okay? And since the initial velocity here is 0, this guy has 0 kilogram meters per second initial momentum. And we know the initial momentum of this guy, I'm skipping a step and not putting in the actual numbers. I'm just putting in the momentums because they're the same thing. 1,200 times 15.6. 1,200 times 15.6 we established is 18,720 kilogram meters per second. And that's equal to the combined masses 1,200 plus 1,500, 2,700 V final, right? So the initial momentum of block A plus block B, the total initial momentum is this. And we're going to divide that by 2,700 kilograms. And what we get, the kilograms cancel out, and we get 6.93 meters per second. And that is our final velocity. Divided both sides by that. So it looks like D is our answer to this. So that's a good example on, so you can see this is a little bit easier, actually, because you have only one final momentum, right? Both objects have been combined, and now it's just only one final momentum, right? So inelastic problems are a little bit easier than elastic problems, in my opinion. Okay. And again, see how easy that was to do? There's only one unknown. It's really easy to analyze this if you've storyboarded it and you've labeled everything correctly and you've put your vectors on everything and you've done your momentum bar charts. You could actually pretty accurately get what the answer is before you actually do the formal summation of momentum and do your equations. So it's always good to find out where you're going before you actually get in the car, right? Well, there's another type of, so that's one type of inelastic collision when you have two objects separated and then they hit and combine. Well, this is another type of, there's another type of inelastic collision where the two objects are together in the beginning, right here, and then afterwards they're separating. So it's almost the reverse of this. They start off in the beginning and then they separate. So this is an explosion, essentially, a rocket a rocket flying up in the air is basically just an explosion, right? It's got the fuel and it's got the rocket itself sitting there, and the fuel starts to explode. The fuel gets forced down, so it's got a momentum that's down. The rocket, by that same explosion, is going to have the same force up, which now it's going to have the same momentum up. And that's an extension, again, of Newton's third law, right? So this is a part where the two objects are together in the beginning, and then in the end, they are separated. Okay? So let's try it. Let's try it. This is going to be a cannon problem, though. We're going to use a cannon. You've got a cannon that's 1,200 kilograms, and you have a cannonball that's 100 kilograms. So they're in the beginning, they are not moving. They're just together at stationary. Then in the end, the cannonball is going to be shot out to the right at 35 meters per second. And we want to know what is the recoil of the cannon being shot to the left, the cannon itself. So what I want you to do is try the entire process, storyboard this, put your vectors on, label everything in accordance with the coordinate system, label what your unknown is with a question mark. Do your bar charts, okay? Again, we're going to adjust our bar chart here. This is considering there's two systems, and this is just going to be the cannon. I'm going to label this cannon and the ball. Cannon is C, the ball is B. This is a cannon, and this is the ball. All right. So go ahead and actually, I should have done that in reverse. This is the cannon plus the ball in the beginning. So this isn't here. And now the cannon is over here and the ball is separating. Remember, together, so this doesn't exist. There's just one momentum in the beginning. And now there's a cannon and the ball at the end. All right, so go ahead and try this out. And try to get it from beginning to end and try to select an answer. Let's see how well you do. Please pause the video now. All right, let's go back. So let's go ahead and label this. I'm going to give it a big old block and call it the cannon, and the ball are together. So this is the cannon and this is the ball. And rather than this, I'm going to put the ball here and label it with a B. And this is 1,200 kilograms plus 100 kilograms, right? And initially it says we had talked about they are not moving. Okay? So initially, the initial velocity of both things, they're both 0. Right? Which means the initial momentum of the system is 0. Now there's an explosion. Okay? You've got the cannon here, and you have the ball over here. The ball is going to be moving to the right with a final velocity of a positive 35 meters per second. And this is the ball's mass, which is 100 kilograms. The cannon is going to be moving to the left at some final velocity. The cannon is the question mark, right? And it's going to have a momentum backwards. P cannon final. And this is 1,200 kilograms, right? Well, let's see what we're working with here. We know the final momentum of the cannonball is going to be 3,500 kilograms meters per second. And that's the final momentum of the cannonball. Okay? That means this has to also work out to be 3,500 kilograms, right? Because this is 0. What might help is if we label this, right? So I'm saying this. If this 3 blocks is 3,500 kilograms, this has got to be 3 blocks final. And that's because so this system doesn't exist, so we're ignoring that. Remember, the initial momentum here is 0 kilograms meters per second, right? So that total initial momentum is 0 kilograms meters per second, right? Well, that's got to work out to be the total final momentum has to be the same thing, right? And if the cannonball is going to have a momentum of 100 kilograms times 35, which is a positive 3,500 kilograms meters per second, then this guy's got to have a negative 3,500 kilograms meters per second. And what that means is that this final momentum here, which is P final, that P final there, this guy is going to be negative 3,500 kilograms meters per second, and that's equal to its mass, which is 1,200 kilograms times its final velocity, right? Well, that means it's going to be negative 3,500 kilograms meters per second divided by 1,200 kilograms. That's going to work out to be, let's find out. Let's go ahead and just do, was that 3,500? I'm going to make it negative kilogram meters per second divided by 1,200 kilograms, negative 2.92 meters per second. So this should work out to be negative 2.92 meters per second as a final velocity. That is what we are estimating this guy to be. All right? That's what we're estimating this question mark to be. Well, let's try it out. P initial, P final. Okay? The initial momentum of the cannon plus the ball is equal to the initial momentum of the cannon, the final momentum of the cannon plus the final momentum of the ball. Okay, and what we found out that this guy is 0. So this is going to be 0 kilogram meters per second, and that's equal to the final momentum of the cannonball, the cannon, which is a mass of the cannon times its final velocity, plus the final momentum of the ball, which we found right here, which is 3,500 kilogram meters per second, right? Again, this is from 100 kilograms times positive 35 meters per second, right? And 1,200 kilograms, and that's VC final. I'm going to subtract this from both sides. Kilogram meters per second. And so what we're going to find out is that VC final is equal to what our estimate was over 1,200 kilograms, which is going to be negative 2.92 meters per second. Okay, so it looks like the answer is going to be C to this one. And that's right. So this is an example of the other type of inelastic problem. Well, there's a similar problem that Knight has done in his textbook. Okay, you've got a ball, and the ball is basically in a tube by a compressed spring, and the spring is released, they both explode, right? And springs are considered mechanical energy, which is a conserved, it's a conserved force, so it's going to be the net force, the ball on the spring attached to the tube is going to be equal to the force of the spring on the ball. So they're going to be equal and opposite forces, so it'll be contained. And so that's what he's saying here. The whole net force is going to be 0. And he drew it out. He labeled it just like we did. Equal and opposite forces. Okay. And then he's listing out his momentum part. And then he solved for it right here, right? So we're going a little bit further than Knight is by creating our momentum bar charts. And that actually really does a good job at helping me visualize what the problem is in terms of momentums. So I want you to try all that when you go through your sapling homework, okay? Thank you very much for listening to this, and go do the lecture tutorial and labs associated with this, and then try the sapling homework after you attempted those. Thank you very much.